Welcome everyone, and I'm very happy that you survived the last night party. Cool, that's always nice. Today we start with Sebastiano, so big round of applause.
Hello everyone, welcome. I am Sebastiano, I work at JetBrains and I'm an Android GD as well. So what we're going to be talking about today is static analysis mostly. I know there's been a talk about static analysis yesterday. There's some minor overlap with that, but we're going to be going a bit more into details, so not too much of a deal. So what is static analysis? Static analysis is a good way to make sure that, the stupid silly bugs that we all at some point introduced in the code base, it's a way for us to catch them as early as possible and avoid repeating those mistakes. Because after all, what we all strive for, or we should be striving for, is code quality. Code quality is not just a word, it's really important because it's the only way we can ensure that we know what we ship and what we ship works. It also implies consistency, and again, it's really important that you don't waste your time fixing the same issue multiple times because maybe you have a regression, maybe you have something really, really silly that slipped in, and we really want to minimize any problems that we might be having. And a great way to do that is having less bugs in the first place. So we really need some sort of a safety net, something that helps us avoiding these mistakes. And how do we actually get there? What do we do? So what is our baseline and how do we get there? There's three main things: testing, static analysis, and CI. Now, testing, do test. Please do test. If you haven't written any test in your code base, please go after this talk, write some tests, and then tweet me a picture of your test passing. Do both unit and integration tests, at least try to. But testing is a huge, massive topic, and we're really not going to go through it today because that would be a talk in and by itself, or actually multiple talks in and by themselves. So let's jump into static analysis instead. Now, what is static analysis? Well, static analysis is what we get with a set of tools that analyze code statically. What does that actually mean though? Because that's the tautology. But that means that we look at the code when it's at rest. So the same way our human eyes could look at the code and then some. We use static analysis to check for common bugs, for oversights, missing comma here, unnecessary column there, that sort of stuff as well. And it might or might not, depending on the tools, involve analyzing the generated bytecode. So it could be just looking at the code, just the same way we could do it, but it could also be looking at the bytecode, the Java bytecode, the class file, the text file, whatever. And there's a bunch of code of static analysis tools that also look for code style violations. Now, as Android developers, I don't know if there's any iOS developers here. There's a bit of an intro here which is very Android specific, but I think that the general idea works for everyone. Android developers come from Java, historically. Some are unfortunately still stuck on Java 8, which is quite old at this point. Java has a lot of static analysis tools because it's been around for a long time. And the nice thing is that a lot of these tools, well, most of the ones at least that you would have used as an Android developer, are free or open source even. There's also a lot of commercial, highly specialized tools, for example, security, for example, any sort of thing. But let's look at what I used to call the holy trinity of Java static analysis. Most of you will know these. Find bugs. Actually, find bugs hasn't been developed for a long time. Just use spot bugs, which is a fork and is actually maintained. There's PMD, and there's check style. These are the main three static analysis tools that you would use if you were doing Java. There's also a lot of others. There's Android Lean, there's Facebook's Infer, there's Google's Error Prone, bunch of them, really. Just pick one, go for it. There's others. And also, because I work at JetBrains, don't forget about your IDE. So your IDE is actually really good at helping you write better code. Android Studio and IntelliJ are full of the so-called inspections that are something that analyze your code both in the editor and so-called offline, which is on demand, when you say, okay, now check all the code and tell me if you see anything that is weird. So they both have a way to work which is very similar to other static analysis tools, which you just kick off at some point and then see what comes up, and also tells you in real time what's going on. And also the IDE has a really powerful code formatter for Java, which can help you get to some level of consistency in your code style. But what about Kotlin then? Because we've talked about Java, but the situation is not exactly the same. So there's some good to it. Mostly Android Lint works. There's been a lot of work from the Android Lint team a year or two back, where they basically ported the whole Lint engine from one older set of APIs for parsing the syntax tree to a newer one. And that newer one also supports Kotlin. So Android Lint is probably the most, let's say, well-developed static analysis tool that we get on Kotlin. It is Android specific, but some stuff actually works on Java as well. And you don't need to only run Lint on Java JVM only projects. And again, IDEs still have inspections. Now, they're not as many, they're not as complex as the Java ones, but it's improving. Again, remember, Java's been there for a long time, tooling for Java's been there for a long time. Kotlin is still relatively new-ish, but it's gotten popular in more recent times. Now, what's bad? So basically nothing else works, which is kind of a pain, because obviously we are used to a lot of this tooling. There's a lot of stuff that was extremely useful in the Java world that at first glance you don't really get. You just try to run check style, PMD, find bugs on a Kotlin code base, they're going to blow up in all sorts of ways because they don't expect Kotlin, they're made for Java. There's no first-party tools from JetBrains if you don't count the IDE inspections, which is officially the static analysis that JetBrains provides. And there is, let's say, room for improvement for the IDE formatter. It's there, the basics are covered, but obviously it's not as mature as the Java one. Still improving everything, but it's not as strict as the Java one can be. So there's a bit less enforcement that you can do on the code style. But there's some hope. Not all hope is lost at this point, because there's some third-party tools that, as developers that do Kotlin, we can use. The first one is KT-lint, which is an anti-bike shedding Kotlin linter with built-in formatter. We'll see what that actually means in a second. Then there is Detect, which is static code analysis for Kotlin. Those are just the taglines from the GitHub repos, simply. And then there's SonarQube, which is sort of a mixed bag at this point. So KT-lint, that mouthful, what does that mean? So anti-bike shedding. I don't know if you're aware what bike shedding means. It's basically when a team gets caught up in a sort of pointless discussion about futile aspects of a code base. For example, well, in a project, it could be, we're building this massive building, but there's a shack for the bikes in the courtyard, and what color is that going to be? Because that's really important. We don't care about the building, we don't care about the plumbing. That has to be yellow. And that's the same thing that, as developers, we've seen. Like people will say, oh no, you need to use tabs. Oh no, you need to use 2 spaces, 4 spaces, Hungarian notation, no Hungarian notation. So all those things we want to get rid of as much as possible. There's very clear guidance on the code style for Kotlin that we should be following instead of wasting time on that stuff. So KT-lint helps us avoiding these discussions by basically not allowing you to customize it in any way. Like you cannot customize it, just run it. It's green or it's red. It's a linter. Now, a linter is a tool that verifies code quality and checks for potential smells or suspicious code. And Kotlin only looks at the source code. It doesn't do anything else than that. It doesn't look at bytecode. It doesn't do. It's just the most simple sort of linter. You could say in a way that is equivalent to check style, just not as configurable. And it follows the Kotlin official style guide, which is on the Kotlin website, and also supports the Android-specific Kotlin style guide, which you might or might not be aware is slightly different from the official Kotlin style guide. There's just if you're using it from the command line, it's just --Android. But if you're using a Gradle plugin, there's probably just a flag you need to set in the configuration closure. And it can fix many of the violations by itself. The trivial stuff, at least, like too long lines, maybe not, because it doesn't know where to break them, and it lets you do that. But stupid stuff like, you forgot a space after a comma, it's gonna fix it for you. So it's very valuable for that, because it's kind of like, it covers some of the same scenarios that the code formatter in the IDE does, but runs on the command line and does actually some more things to enforce the code style, which is very valuable. There is some sort of a configuration. You can do some very minimal degree of configuration you can have with Kotlin. You just have a .editor config file in the root of your repository, and that file can be used to tell Kotlin what is the maximum line length that you want, and if you want to use spaces for indentation or tabs, and how many spaces is your indentation. That's the maximum degree of configuration that you can have, which is not a lot, but is enough. Has to be. Now, the next tool we said is detect. It's a static code analyzer, which is a bit more of a generic term, and it is more similar to what PMD and find bugs would do in the Java world. It inspects both the code, the source code, and the abstract syntax tree that is built from there. And it does, just like Kotlin, it does not actually look at the compiled bytecode. It does have some understanding of the code, but the understanding of the type system and the types of things is somewhat limited, which limits the efficacy in some cases and can bring up some false positives. They're working on improving that, so at some point it should be there. Contrary to Kotlin, detect is configurable in depth. There is a YAML file that is contains the whole configuration. There's a default file that you can find in the detect repository, or you can also use a Gradle task that the detect plugin creates, which is detect generate config. That's going to write out the YAML file with all the defaults for you. My personal recommendation is to use that, which is build upon default config. It's an option that you can pass to detect to say, okay, take the default configuration and patch in whatever things I tell you onto that. So you don't have to specify the configuration for everything with all the defaults. You can only have the handful of rules that you want to tweak. So that's very useful. That's available from RC13, if I'm not wrong. So you need to use a relatively recent version of detect for that. So that alone is probably worth upgrading if you're stuck on an older version, plus all the bug fixes. There is also an IntelliJ platform plugin for IntelliJ IDEA and Android Studio. It shows the violations in the editor. I find it a bit noisy, but it can be valuable if you want to have that sort of analysis immediately, and it can be useful if you get used to it. Lastly, we mentioned there's SonarQube. SonarQube has an amazing Java support. It's great. It's probably one of the best things out there. The problem is that Kotlin is only kind of supported. It's a relatively recent addition to SonarQube. It's had support for Swift for a long time, but Kotlin is quite new. And the way it supports Kotlin is it uses Android lint and detect. Now, the difference is from Java, for example, SonarQube, besides using other tools, like it can look at the output of check style, PMD, find bugs, whatever, but it also has built in a lot of rules and a lot of checks that are incredibly valuable. Those are not there yet, at least not last time I checked, but I think they're going to get there eventually. It is not nearly as comprehensive as other languages, though, unfortunately. But it's still very good to have it if you're in the process of migrating a code base from Java to Kotlin. Because, for example, besides all the good stuff you get on Java, you also have a unified dashboard where everything sits, and you can see at least some of the things that Android Lint and Detect would pick up, all in the same place as Java, and you get a unified bugs count, you get a unified number of issues and estimations of fixing time and so on and so forth. So it's still useful. So static analysis, what we said is there is some good stuff for Kotlin out there. There's no excuses not to use it at this point. Now, it's not as good as Java, the situation, but Java's been around for 24 years. The IntelliJ platform has been around for 19 years, and the Java support is as old as the IntelliJ platform. So obviously, tooling is not at the same level, and Kotlin is also not as widespread, although it's in the top fastest growing languages in many Stack Overflow yearly reports and stuff like that. So I'm counting on it to become more widely adopted, and thus tooling improving a lot. But it needs time to catch up with Java. And lastly, and most importantly, do listen to your IDE inspections and make sure that you use all the tools that you have, because we have a few and we must take the most out of them. Now, we also said that the third column to achieve code quality is CI. Now, CI means, as probably most of you know, continuous integration. It is hardly a new concept. It's been around since the 90s. It was actually popularized by extreme programming, also known as XP, not to be confused with Windows. And again, I'm going to be very tautologic here, but the idea of CI is to continuously integrate any changes that you make into the main branch of your work. So for example, make sure that everything that you do is integrated as quickly as possible into master. Avoid long-running branches, avoid all the problems that get with having to merge. There's the one developer that takes on a story and runs with it for 2 weeks, and in the meantime, the same code that he's working on, or they're working on, it gets changed, and at some point, they have to merge back into the main branch, and then they have to spend another week fixing all the problems that come up when they have to merge, and they have conflicts and problems of any sort. And the main advantage of this practice is that it allows you to catch those integration issues as soon as possible. To make the most out of continuous integration, we will need to leverage everything we have at our disposal: the build system, the compiler, the tests, and the static analysis. Because all those things are what allow us to find out what's going on, what are the problems, as soon as possible, and fix them while they're still small. Now, continuous integration, it's actually a practice. We are kind of used to refer to continuous integration as the services we use, but theoretically it's a practice. Now, there's software, there's services that allow us to do continuous integration. But what we do use generally are CI servers or CI services. For example, Travis CI, which is a sponsor here. They are a service that allow us to implement continuous integration, which is a practice. Why should we, though, be adopting CI? Oh, also, I'm going to be saying CI from now on. I mean it in the general case of service that implements continuous integration as a practice, because that's too long to say. Now, why should we adopting continuous integration? Well, the first point and the most important thing to me is that it takes out the human factor. Humans are humans. People forget to run static analysis. I do. I forget to run tests before pushing all the time. But if I have a CI, I know that's not really a problem, because before anyone can say, that looks good to me, merge it, well, the CI is going to be like, you fix that first. So that's really important. And also, it allows us to save our time. we all know the xkcd compiling strip. We don't really want to do it that much because obviously, besides the fact that it's really boring, but the continuous context switching that you get is really killing your ability to focus on things and solve problems. And saving devs time, besides the monetary advantage of it, which is obvious, but is also good for us. Like it keeps us more focused, it keeps us more in the zone and helps us deliver more better. And the other advantage of CI is that you can run all sorts of things on a CI service, both on demand and with a schedule. Examples might be running the CI every time someone pushes to a branch, or running the CI every time someone pushes to a branch that is involved in a pull request. Or maybe just running every night, you run a bunch of things that take forever. You don't want to run them all the time, but once a day is fine. So you can have nightlies, you can have nightly builds without anyone having to go there and remember to push the button. It's just done for you. That's super useful. Now, as I mentioned, CI is a practice and there's services that allow us to implement it. Now, there's two main kinds of CI services, self-hosted and in cloud. Those are the names I gave to them, but I think they give a good idea of what is what. So self-hosted first. Examples, Jenkins, TeamCity, and others, but I would say Jenkins and TeamCity as an Android dev are the ones you're going to be seeing the most. You generally see Jenkins in smaller deployments and TeamCity for more enterprise. They are more enterprise friendly than the cloud alternatives, mostly because they're sitting generally, well, they can be sitting inside of your local network. So if you're at the office and you have a very strict set of rules for avoiding, for example, your code being exposed to the internet, well, obviously you kind of use a cloud service because it's never going to be able to get to your code and run whatever it needs to run. So something on premises, on a server that is installed in your physical building and it is physically located inside of your local network, that's invaluable for an enterprise. And also by the fact that you control the whole stack, you control the machine, you control the software that runs on it, you can do whatever you want with it. It's way more customizable. Now you can also run self-hosted stuff on, say, Amazon instances or Google Cloud instances. It's effectively the same, but you lose the main enterprise friendliness point at that situation. So the main drawback of this sort of setup is that they require a lot of time to set up, they require a lot of time to maintain. Especially if you have a CI that is exposed to the internet, you really don't want to fall behind on security patches because the CI contains your server, your code, and if someone gets access to that server, they have access to your code, which is absolutely something you don't want to do unless you're running an open source based company, in which case, Now, in cloud, on the other hand, there's a bunch of them, really, too many to list here. There's Travis, there's CircleCI, there's Bitrise, there's GitLab, there's Google Cloud Build, some come and go. There used to be stuff like Buddy Build that has been bought by Apple, and then they said no more Android there. So again, there's risk with that. Obviously, you don't control the full stack. The company might close down at any point, so there's some risk there. But they're way easier to adopt because, especially as an individual or a small company, you have very little to do. You don't have to care about building the hardware infrastructure. You don't have to care about maintaining that infrastructure. The systems that run the thing are somewhere else and someone else's problem. So it's very easy to set up something hosted in cloud. On the other hand, again, if you cannot access the internet from your local network, then you're out of luck, you cannot use them. And at the same time, they can be costly because, let's be honest, in cloud services, because of the fact that they take out so much work from you, which is still work you would have to pay otherwise, that you would have someone that does DevOps for you if you want a proper CI setup. Or you would need to put some time of some engineer on that. So obviously it gets costly, but it's providing a lot of values. And there's also some services that kind of blur the lines, which are can be both self-hosted and in cloud. A good example is TeamCity. Buy it. But again, if you don't have cache, you don't need to worry. You can try out most CI services anyway, because most of them offer a free tier. It could be it's free for open source projects. It can be you get a certain number of build executors for free, regardless. You can get a certain amount of CPU time a month, or you can get like a free license for up to N users. There's many ways to try out services without paying. Now, we talked about the CI services, but what is actually, how does a CI look when you're working with it? The CI is generally made up of nodes. Now, there's a master node, and there's executors or agents. The master node is simply the node that orchestrates the jobs, is where the jobs are scheduled, and it decides you do that, you do that, you do that. It's basically the manager. And then there are agents and executors, which are the actual nodes that are generally a bit more grunty, that have the task of running stuff. They're generally Linux in most cases, because it's cheaper. But obviously, if you do iOS or macOS, you need to have macOS. And if you do Windows, you probably want to have a Windows node or many Windows nodes. The way executors work is that there is a build queue. And as you create new work for the CI, then the build jobs are posted to it. And as soon as the CI is free and there's a job posted to it, it's going to start working on it. Then more get posted, and then obviously it's a queue. It goes on, works on stuff until the queue is empty again. Now, a typical job I mentioned is composed of several things. For example, in a typical Android app, it could be running assemble, running test, running lint, running static analysis. This is Kotlin, so detect and kt-lint. This is generally done just for release, but maybe your setup has multiple flavors that you want to run this for. And in that case, that stacks up, and you're running the same stuff a bunch of times for different flavors. At that point, it might come to you saying, oh, actually, I could just run the build task, which unfortunately is very, very big. So it's going to take forever if you run that. Now, a better way to look at this could be splitting the work and saying, okay, these are the main things I want to run. And then if you do that, then the CI is going to be like, okay, I'm going to run this, then I'm going to run this, then I'm going to run this, and I'm going to run that. Unfortunately, this is going to take a very long time. I timed it right. What if we could say, actually, my CI, my node has got 4 cores. So why don't I just post one thing per core and run them at the same time? Obviously, it's going to take way less. What if we could do that? Well, actually, we're in luck, because in CI, there's a concept of a pipeline. A pipeline is, simply put, a group of jobs executed in stages. Now, pipelines can or cannot be parallelized. It really depends on your setup, your needs, and it can take less time to run when they're parallelized than not. I say can because sometimes they actually take more time because of the maybe Gradle overhead, because many factors. But they're supported pretty much by all services in some way or form. Sometimes you will see them referred to as workflows or build chains or other names. But if you're wondering, should I use pipelines? The answer is most definitely yes. Yes, you should. And we'll see why in a second. So let's look at a typical pipeline example. The first step you would do is obviously check out the code. You need the code, otherwise nothing you can do. Another thing you can do is say, okay, I'm going to do a bunch of things. I need to run a bunch of things in parallel, but there's no point in having all of those things download dependencies for the project. Let's just do it. Get it out of the way, and then we can run everything else in parallel. For example, we can run tests, we can run static analysis, we can build APKs, and so on and so forth. It's really important at this point that you do test different combinations, because sometimes, depending on your code base, depending on the service you're running on, it might be better to bulk up a bunch of things into a single step instead of splitting them out. Again, because overheads are different between even just Gradle versions, and plugins you use can make a huge difference. So do try out different things. And I'm going to conclude this talk by looking at a practical example. So this example actually is done with CircleCI. Sorry, Travis. But there's a reason for that. Why is that? Well, simply enough, CircleCI is quite well adopted in the community, just as much as Travis, in the Android, at least, community. Most cloud CIs anyway kind of work the same. Like 99.9% of what I'm going to be saying about CircleCI also works on Travis, most likely. Probably names are different, probably there's some small adjustments to be done, but the ideas are the same. And also I'm lazy and I have an example ready for that, so that's always good. Now CircleCI, like most cloud CIs, is Docker based, which means it's going to spin up containers inside of virtual machines to run your code. It also is configured like most cloud services with a YAML file. We are going to be using version 2.1, which is currently the latest available. And also there's free tiers on CircleCI's. As I said, in CircleCI's case, you get one free Linux executor regardless. If you're doing open source, you actually get 4. So the example I'm going to be looking at is open source, so we get the 4 executors, which allow us to work on 4 things in parallel at the same time if we want to. Our example, we're going to be looking at the code of Squanchy. Squanchy is an open source project that I'm contributing to. It is an open source conference app that is written 100% in Kotlin and has unit tests, but doesn't have instrumentation tests, mostly because instrumentation tests are a pain to set up, especially on CI, and we never had the time to. We want to, but we haven't had time to. So if anyone wants to contribute any, you're welcome. Please do. We use static analysis. We have Android lint, we have KT-lint, and we have the tag. Again, everything we can use, we use. And it's a small app, so it's not very modular. There's only a couple of modules, one of which is copied code that I copy-pasted from another repository because the author was too lazy to fix a bug and update the code that was deployed as an artifact. The author is a friend of mine, so I can say that. Getting started, what do we need? So obviously, we need a working Gradle build, because if it doesn't build, there's no point. We need to identify what are the tasks that we want to execute, both in Gradle and outside of Gradle. Then we need to identify what are the secrets that the application needs to be able to run the build. For example, it could be anything from key store passwords to API keys to anywhere, anything really. And the way we're going to be doing this is environment variables. You can also use the mechanism that most CIs provide you, which is to inject things from the configuration panel so that those secrets are not leaked in the configuration file. But for us, it's fine like that. We're fine with this. So first thing, does it build? Yes, it does. Done. That was easy. Next thing, okay, we need to look at what we do in the build and understand what are the things that we are going to need to do in our CI. First of all, obviously, we need to check out the code. This is not done by Gradle, obviously. Gradle will run after we check out the stuff. Then, as I mentioned, we want to warm up the Gradle caches. We want to warm up all the caches to make sure that all the dependencies are available when everything else runs. Because doing networking is slow and we want to be as fast as possible, because who likes to wait for the PRs to become green or red? And we have a task for that, which is called download dependencies, that just does what the name says. Then we run the tests. We only have unit tests, so in this case we just run test release, easy enough. And then we have static analysis, we just run all the things. Very important, we're only running tests and lint in release, because there's no point in wasting time and running tests and lint in debug. If debug is broken, we're going to notice when we code. And anyway, it doesn't really matter as long as production is fine. Next up is identifying the secrets. In this app, there's 4 API keys: Fabric, soon to be Firebase. And we also use a service called Algolia that is a cloud indexing service that provides search. It's a conference app. You might want to search for talks. That's the service we use. And it needs 3 pieces of information to run. And then we have 2 other pieces of information that we need to pass in. The first is the application ID. This is basically a white label conference app that is meant to be run for multiple conferences. And so the package name really depends on the conferences you're building for. So that's one piece. And the other piece is we use Play Services. We use Firebase and does Play Services. And we are using the Play Services plugin, which requires a JSON file to configure the build. That's really hard to inject as an environment variable. So what we do is slightly different, and we'll see it later. A pro tip here: if you want to have your life made easier, there's a really good plugin by Novoda, which allows you to say, basically, get me this value, but you can get it from there. If you don't find it there, you can look here. If you don't see it here, you can fall back on that and eventually provide a default or allow the build to break if something is not configured correctly. That's very useful because this way we have the possibility of saying, okay, look for this file, this properties file, for example, that is not committed in the repository. Developers will have that in their machine, but the CI will not. But then the CI can say, well, the file is not there, but I have those values in the environmental variables, so I can get it from there instead. That's just a pain to do by hand, so that's really saving you a lot of time. And lastly, we can go on with the configuration. Like we said, it's a YAML file, it lives in the .CircleCI folder, and it's versioned. Again, we're using the latest version, 2.1. And this is how it looks. Can you read that? I don't think so. But it's very easy once you boil it down to the top level sections. There's, again, a version. Quite obvious what that does. And then we have executors. Executors is a section that contains information about how to run the actual job. So the main thing you get in the executor nodes is a list of executors, unsurprisingly enough. In our case, we only have one, which we call Android. We can say, hey, this is actually running in the Squanchy folder in the own directory, and we can say, oh, when you use Docker, you can use one of the built-in Android Docker images to run the build. That's very easy. That's all you need to do with Circle. You just say, use this image or those Docker images to bring this environment up. That's all you need to do. Super easy. And then we have a list of environment variables that the build are going to contain. In our case, it's all like made up stuff except for the Android Home one, which I'm not even sure it's needed anymore, but it used to be needed, and I've never checked if it's still. Everything else, as you see, is like zeroed out. We don't build the actual APK at the end. It's not one of our build outputs, so we don't care about the application actually working. We just want to build, so that's enough. So executors, seen it. Next step is commands. Commands are just a list of steps, and they have a name that is displayed in the web UI of Circle, and then a list of other stuff that really depends on the name of the kind of step. The easiest one I can think of is attached workspace. It's saying, okay, just bring this up now, here in this path. There's 2 other ones, which are save cache and restore cache. Basically, save cache, you can say, take these folders, save them for later, and restore cache is the opposite thing. One important thing to say is workspace only lives in a single workflow run, whereas caches can be recovered in subsequent builds. So you can store, say, Gradle build cache in there or stuff like that, which will speed up subsequent builds. And it's very important, this is a pro tip, when you have keys, just always make sure that they are versioned there, because that allows you to invalidate all the caches by just changing this file without having to go and change other stuff somewhere else. It's a very neat way to say, oh, actually my CI is having a problem, I'm gonna nuke all the caches and see how this works. Or maybe nuke some of the caches. And then lastly, run. Run is another kind of step, does what it says on the tin, runs something, whatever you want. There's 9 commands in our build: save restore, save restore, save restore, and then 2 other utilities, and then restore workspace. They're all very easy, so I'm not gonna spend more time on it. Jobs is a section that contains a list of jobs. Now, jobs, they're again, a list of steps. Steps can be declared in line, just like they're the same thing you would put in a command, or you can use commands directly. So commands are basically a good way to refactor stuff out of your job description, or maybe reuse them in multiple jobs. We have 4 of them. They're the ones we've said in examples earlier, so I'm not going to spend more time on that because I'm late already. And last thing is workflows. Workflows is the thing that ties them all together. It says these are the jobs that the build runs, and these are the dependencies between the jobs. So for example, first one in the list is checkout, so that's what the CI is going to start from. Next thing is prepare for checks. Now, prepare for checks requires checkout, so the CI will make sure that it's run serially after checkout. And then we have static analysis and tests. Now, those 2 depend both independently from prepare for checks, which basically means you can run them in parallel after prepare for checks is done. You will notice this is a directed acyclic graph, which means it's a graph with a direction. It cannot have any circles there, but it's a graph. Like, we all know graphs, probably not as well as we would like to, at least in my case, but we know what a graph is. Now, super quickly, what does happen during a run? We've seen that's the general structure. So checkout runs checkout, sets up the Android SDK, creates a mock version of the JSON for GMS. Again, we don't care about the values because we're not running the app effectively, so any value in there works. And then we persist what we created to the workspace. So basically what we're doing is getting stuff, doing some stuff, and then saving stuff. Next up, prepare for checks. Now, when you do this, first thing is, this is run on a separate instance. Every job is run on a separate container instance, so you need to restore from workspace to get the files to work on. Restore the caches, download the dependencies, save the caches, and persist the workspace. So we're getting all the stuff we had cached previously. If there's no new dependencies, then the third step will do nothing. If there's new dependencies, then we'll get the new dependencies and save the cache, so the next time the build is going to be faster. And again, getting stuff, doing some work, in this case downloading, saving stuff. Last up, static analysis and tests. They're pretty much the same thing, so the structure is the same. Restore from workspace, restore caches, run the tasks, and then store the artifacts. In this case, run task could be running detect and kt-lint or running the test. So again, get stuff, do stuff, save stuff. So if there's one thing that is really important about this whole thing, about practical example, it's these 3 things. When you are writing tasks for your CI, and it's a cloud CI that uses containers, thus all the steps are isolated, all the jobs are isolated, then what you want to do is get stuff, do stuff, build stuff. So in conclusion, what are today's lessons? Static analysis is good. Use static analysis. Continuous integration is good. Use the continuous integration service. And also static analysis is better when you have a CI. And lastly, you can check out Squanchy for a practical example of how this works. I very briefly looked at stuff. You can go into more details. You can ask me questions if you don't understand something. You can find it there again. And that's all. Thank you very much. The slides should be online already. So if you've missed something, because I realized I did run a bit quickly through some stuff, you can find it there. Thank you.
Thank you. And I guess we have coffee break and probably if you're fast enough, you can get some passion to Sebastiano.
Or yeah, now or later is the same.
At the coffee break.
Yeah, let them have coffee.
Yeah. Well, that's for sure. Just fun fact, we copy pasted the configuration from Sponge for I mean, the thing is actually very good. Just
Thank you.
copy paste the thing. Now it works. Enjoy.
Thank you.